Okay, I think we're going to go ahead and get started. Before I introduce today's speaker, just a reminder, our next meeting of Nano Tech will be 2 weeks from today on November 28th. It's pretty unusual for us to have 2 November meetings, usually because of Thanksgiving, but the way the calendar worked out this year, we actually have a 4th Tuesday in November that we can meet on. So that will be here, and the speaker will be Azad Naimi from Electrical and Computer Engineering. So it's a real pleasure to have Professor Seung Woo Lee with us today. He got his undergraduate degree in chemical engineering at Seoul National University, and then moved to MIT, where he got his PhD, and then also did postdoctoral work before coming to Georgia Tech in 2013 to the School of Mechanical Engineering, where he's currently an assistant professor. He's won a number of different awards, most recently from the Samsung Corporation, as well as the Korean American Scientists and Engineers Association. And his research is broadly in areas of electrochemical energy storage and conversion, and we're going to hear a little more about that today.
Okay, thank you for kind introduction. So today, I'm going to show some examples. So how we can design some multifunctional electrode for next generation energy storage devices. First, let me briefly introduce the motivation of this research. So as you know, because of the safety and also because of the environmental issues, so we are trying to replace fossil fuel with the renewable energy sources, such as solar and wind energy. The question is how we can connect this renewable energy source to end-user applications, such as house electricity and electric vehicle and portable electronic device. First, we can directly convert this renewable energy source to electricity using this kind of photovoltaic cell or concentrate solar power, and or this kind of windmill. So then the generated electricity is delivered to end-user application directly through this kind of the electric grid. But as you know, this kind of renewable energy source is intermittent. Basically, we need to store energy during daytime for demand at night. So basically, electrochemical energy storage and conversion device can smoothly link this kind of renewable energy source to end-user applications. So let me first introduce 2 representative energy storage devices. First one is electrochemical capacitors. Sometimes we call these supercapacitors. So when you apply the potential, so one electrode is positively polarized and the other one is negatively polarized. So then oppositely charged electrolyte ion can adsorb on the surface of the electrodes by the electrostatic interaction. So we call this is a double layer capacitance. Basically, this kind of the electrochemical capacitor can store charge on the surface of the electrodes through this kind of double layer capacitance charge storage mechanism. So on the other hand, so lithium-ion battery store charge in the bulk of electrode materials. So these are examples of the conventional lithium-ion batteries, consist of this kind of lithium cobalt oxide positive electrode and graphite negative electrodes. As you can see, both electrode has this kind of layer structure materials. So during the charging and discharging process, lithium-ion intercalate and de-intercalate during the charging discharging process. Basically, we are fully utilized bulk of the electrode material for charge storage. So then, if I further explain the electrode material and their energy storage mechanism, so this is a double layer capacitance. So let's say this blue circle is the electrode materials. So let's say these orange dots are electrode ion. So during the charging, so they can adsorb on the surface of electrodes. As I mentioned, this is a double layer capacitance. To maximize this kind of double layer capacitance, we use this kind of high surface area carbons. So on the other hand, so this kind of the for intercalation reaction, so lithium-ion can penetrate into the bulk of materials. Basically, we are fully utilized this kind of electrode materials. So example is lithium cobalt oxide, layered structure lithium cobalt oxide. So in between, so there are another types of the energy storage mechanism called surface redox reaction or pseudocapacitance. Some organic materials, such as conducting polymer, actually they can store charge based on the adsorption of anion on the backbone. So we call that is the surface redox reaction. Also some inorganic materials, such as ruthenium oxide and manganese oxide, actually they can store charge on the surface and the near surface region. So here, so electrolyte ion can penetrate into the little bit of these materials. So penetration depth of this pseudocapacitance material is around tens of nanometers. So based on this charge storage mechanism difference, we can expect the performance difference of the energy storage devices. So this plot called the Lagrange plot, compare specific energy and specific power of the different energy storage devices. So specific energy means how much energy we can store per unit or mass of device. And specific power means how quickly we can deliver or how quickly we can charge the energy. So as you can see, so electrochemical capacitor have high power for low energy. So think about the charge storage mechanism. So this kind of the electrochemical capacitor, ion, or dissolve on the surface of electrode, right? It is very fast, right? So power is very high, but we only utilize the surface of electrode, right? Energy is limited. So on the other hand, lithium-ion battery has a high energy because we are fully utilize bulk of electrode material, but lithium-ion need to penetrate into the bulk of materials. So we call this is the solid state diffusion process. So this kind of solid state diffusion process is low. So we have low power. So then our research goal is to design the electrode materials which has high power, so as much as this kind of capacitor material, and also high energy, so as much as this kind of lithium-ion battery materials. So this is the performance of the lithium-ion battery. So from the 1990, so the energy density is around 100 watt-hour per kilogram. So these days, the energy density is around 200 and 250 watt-hour per kilogram. But this kind of lithium-ion battery is still expensive. So cost per battery pack for electric car is around 500 per kilowatt-hour in 2014. So these days, people estimate that the current is dropped to $200 per kilowatt-hour, but it is not sure. But Gigafactory cost target is $100 per kilowatt-hour by 2020. So based on this kind of energy density and high cost, recently Nature journal raised the battery 4 big questions. The first one is, how do we make battery less expensive, right? So simply we can increase the energy density or we can use the much cheaper materials. And also, how can we make battery that store more energy? So this relates with the energy density. And how can we make a battery safer? So basically, this is related with the safety issue. And the last one is, are battery enough for renewable grid? For example, to store renewable energy, right? So battery should be large, and also battery should be made of very cheap materials. Basically, we need to use some sustainable and much cheaper electrode materials. So this is this picture shows the history of the rechargeable battery. So from the lead-acid battery to nickel cadmium, so these days lithium-ion battery. So this figure prepared by the Professor Tascon, so in 2008. So basically he predicted that, so these days we are using this kind of the nanomaterial-based lithium-ion battery. He already predicted the future of the rechargeable battery. So he predicted that, so probably in 2015, probably we may use this kind of the organic type, so lithium-ion battery. So basically, organic material can be prepared or extracted from this kind of the fruit or some kind of biomass. So this kind of the organic material, especially this kind of the oxygen functional group, can react with lithium-ion, basically can store 1 electrons per this kind of carbonyl group. So then, if I consider charge storage mechanism of this kind of organic electrode material, first, there are p types of the charge storage mechanism. So this is for conventional conducting polymers. So conventional conducting polymer, so if we remove 1 electrons, so we can store 1 anion on the backbone of this polymer. We call this the p-type or anion doping or anion insertion charge storage mechanism. So on the other hand, n-type charge storage mechanism directly react with lithium-ion, so can store 1 electrons. So one of the most representative example is this kind of organic carbonyl compounds. So this kind of carbonyl molecule can react with lithium, we can store 1 electrons. So here is the one example of the p-doping conducting polymer. So this is the pyrene. So basically, this kind of pyrene material is readily available. So during the fractional distillation process of the crude oil or coal tar. So if we dissolve this pyrene in the organic solvent, so if we apply charge, so we can remove 1 electrons, right? So applying potential, removing 1 electrons. So then we can create this kind of the cation radicals. So then this kind of cation radical is coupled with another one, can generate this dimer. So if we repeat this, so we can create a pyrene polymer on the substrate. So then, so we can see during the cycling process, gradual increase of the charging and discharging process. So gradual increase of this kind of oxidation and reduction peak. So this is related with the electrochemical polymerization process. So after synthesizing a pyrene polymer, so we can transfer to the fresh electrolyte. So there's no pyridine monomer anymore. So then if we measure see cyclic photometry again, so we can see clearly oxidation and reduction peaks. So this is related with the anion adsorption mechanism on the this kind of polymer. Basically, we can store 1 electron per each monomer. So then, if I introduce endoping type oxocarbon cathodes, so let me first compare with the conventional inorganic cathode. So this is the lithium cobalt oxide lithium-ion phosphate. So this is a conventional cathode material for lithium-ion battery. So as you can see, this kind of inorganic material have a capacity around 150, 60 milliampere per gram. So their redox potential is around 3.5 and 4 volt. So then, if we see this small molecule, this is introduced by Professor Tarascon group, so in 2008, this small molecule has 4 carbonyl group. So then each carbonyl group can react with lithium-ion, can store 1 electrons. So then, so this is a charging discharging profile of this oxocarbon salt. We can clearly see this molecule can store 4 lithium per each molecule. So then, if we calculate the capacity, it is pretty high, more than 400 milliampere per gram. So if we compare with this organic molecule with this kind of the inorganic cathode, you can see energy density is more than 2 times. But there are critical challenges of this kind of organic materials. The first one is this kind of organic material is insulating, right? So basically, their power performance or rate performance limited. So if you can see, if we increase the charging discharging rate, so their performance is quickly decreased. That's the first issue. The second issue is the low cycling stability because of the dissolution of this molecule during the cycling process. So basically, in the initial, the first capacity is pretty high, 400 milliampere per gram. So within 10 of cycling process, actually these molecules are dissolved in the organic solvents. So we are gradually lose this capacity. So basically, this kind of low rate performance and also poor cycling stability are critical issues of this organic type battery materials. Okay, so from now, actually, let me introduce how we can improve or how we can solve this kind of the issues of organic materials. The first topic is the functionalized carbon nanotube electrode for high power energy storage application. So let's see. Let's say this is the organic molecules include this kind of carbonyl functional group. So we can expect this kind of the redox reaction with lithium-ion. But this molecule is insulating, so we have low power, also poor cycling stability because of dissolution. So then, so we need to mix with a lot of the conductive carbon materials to fabricate electrodes. So then, our strategy is to incorporate the oxygen functional group on the conductive carbon matrix, such as carbon nanotubes. So this is a schematic of carbon nanotubes. So we are trying to chemically incorporate this kind of oxygen functional group on top of this carbon nanotube via covalent bond. So then this kind of carbon nanotube can support high electrical conductivity, right? So then this can improve the power performance. And also this kind of molecules now attached on the substrate, on the surface of carbon via the covalent bond. So we don't need to worry about the dissolution of this kind of organic molecule. So then, so this is schematic of the multi-wall carbon nanotubes. So functionalized multi-wall carbon nanotubes. So we are oxidized the surface of carbon nanotubes. So basically, if we see surface, there are many oxygen functional groups on the surface of carbon nanotubes. So then, so as you can see, we can see this kind of sp2 conduction wall over this multi-wall carbon nanotube. This can be good electron conduction channel. And on the surface, there are many oxygen functional groups, so they can react with the lithium-ion, can store 1 electrons. So this is the basic design principle of this kind of the functionalized carbon nanotubes. So then the question is, how can we incorporate oxygen functional group to the carbon nanotubes? So we use the chemical oxidation process using the acid mixture. So this sulfuric acid, nitric acid mixture, so we are refluxing carbon nanotubes. So at 70 Celsius, by controlling this kind of the refluxing time, so we can control the amount of oxygen functional group on the carbon nanotubes. So here, XPS, so this is a pristine carbon nanotube. Oxygen to carbon atomic ratio is very small, 0.01. Negligible amount of oxygen functional group. But if we increase the oxidation time 2 hours, 4 hours, so we can increase the oxygen to carbon ratio up to 0.2. So then after 4 hours, this is saturated. So then if we see a high resolution XPS, carbon on X peak, so we can see the gradual incorporation of oxygen functional groups such as carbonyl group and also carboxylic acid group, also so another types of the oxygen functional group. So this can also change the dispersion property of this carbon nanotube. Generally, carbon nanotube is very hydrophobic. So we are trying to disperse in water. So they agglomerate, so quickly precipitate in the water. But if we incorporate oxygen functional groups, so their surface become hydrophilic. And also some of oxygen functional groups, such as carboxylic acid group, have some negative charge on the surface. So we can get some kind of the colloidal dispersion, so colloidal stability if we increase the oxidation time. So then, for this experiment, we used the fewer carbon nanotubes. So this carbon nanotube is average wall number is around 3 and 4. So the diameter is 6 to 10 nanometer, and the length is 0.4 millimeter. It's pretty long, actually. Aspect ratio is around 50,000. So this is the pristine fewer carbon nanotubes. So if we see this pristine carbon nanotube image, we can see the wall number is average 3 and 4. So then, after oxidation process, you can see the surface of this carbon nanotube become roughened. So can you guess why? After oxidation process, actually the surface of the carbon nanotube become roughened. Any guess? So basically, to incorporate the oxygen functional group, right? So basically, oxygen radical attacked the carbon nanotube surface, right? sp2 conjugation network is now broken. So by incorporating oxygen functional groups, so now actually sp2 conjugation carbon converted to sp3 carbon, right? So basically, so we are breaking the surface of carbon nanotubes. So we are incorporating the oxygen functional group. So then, if we measure electrochemical characteristic of these carbon nanotubes, this is the pristine carbon nanotubes. So we measure this CB cyclic voltammetry from 1.5 to 4.5. So we use this for cathode or positive electrodes. So this shows almost this kind of box-like shape. So basically it shows potential independent current response. This is a characteristic of the double layer capacitance. So then if we incorporate oxygen functional group, let's say 2 hour and 4 hour, we can see gradual development of the oxidation and reduction peaks, right? So oxidation reduction peaks means Faraday reaction. So charge storage reaction mediating some electron transfer. So we can expect this kind of the redox reaction, so between this introduced carbonyl group and the lithium-ion. So then if we calculate the capacity, so pristine carbon nanotube shows capacity around 30 milliampere per gram, so pure double layer capacitance. But by incorporating more oxygen functional groups, we can increase capacity up to 120 milliampere per gram. So please remember that the conventional cathode material, inorganic cathode, have capacity around 160, 170. Right? Now we are 120. Okay. So for this kind of the chemical oxidation process, so we use the strong acid mixture. For example, so we use the 70% nitric acid and 96% of the sulfuric acid. So as you know, this kind of the strong acid mixture can cause environmental and safety issue, right? So to replace this kind of process, we developed a new oxidation process using much dilute nitric acid. So this is the nitric acid concentration is around 0.15 to 0.3 mole. So instead of the chemical refluxing, so we apply the hydrothermal oxidation process. So we first prepare this kind of single carbon nanotube film. So then we put this film into the closed vessel. So in this kind of dilute nitric acid solution, we just heating. So then, we can create the oxygen radical and attack this kind of the carbon nanotube. We can oxidize this kind of single carbon nanotube film. So then if we see the morphology of the single carbon nanotubes, as you can see again, the surface of these single carbon nanotubes become roughened after oxidation process. So one of the interesting is actually the density also increase. So the density of this single carbon nanotube is around 0.6 gram per cc. But after oxidation process, this density has been increased to 1 gram per cc. So when we design the electrode material for energy storage device, this kind of density is also very important engineering parameter. So can you guess why? Why this kind of density is important for designing electrode materials?
To get the high power density?
So basically, we can get high energy and power density per unit volume of this device, right? So if the density is high, so we can make very thin or very small energy storage devices, right? So then, let's see surface chemistry. So pristine oxygen or pristine single carbon nanotubes has oxygen to carbon ratio is around 0.06. So we can increase this ratio by increasing oxidation time or by increasing the concentration of nitric acid. So up to 0.06, right? So then we can see incorporation of the various oxygen functional group, including carbonyl group. And also interestingly, if we increase the concentration of nitric acid, let's say 0.3 more, we can see this kind of nitrogen doping. So we can see the incorporation of the various nitrogen functional group in the carbon nanotubes. So then, we compare charge storage performance of the singular carbon nanotube and oxidized carbon nanotubes. So as you can see, if we incorporate the more oxygen functional group, we can see clearly the development of oxidation and reduction peak. So this CB compared based on the unit mass of the electrode, right? Then if we compare this CB, the current normalized by the unit volume of the electrode, you can see the further increase of this current because of the densification process during the hydrothermal oxidation process, right? So then this is the gravimetric capacity and volumetric capacity. Now the capacity has been increased to 150 milliampere gram. So then, if we compare the singular carbon nanotubes and oxidized singular carbon nanotubes based on mass and based on volume, so we can see, so we can get high gravimetric and also high volumetric capacity around 150 milliampere gram or 100 ampere hour per liter. Okay, so this is the related with the carbon nanotubes. So let me switch a little bit. Let me switch the topic to graphene materials now. So these days, so we can prepare graphene oxide from graphite. So using the chemical oxidation process called the modified Humboldt method, right? So we can prepare large scale of the graphene oxide from graphite. So this is the graphene oxide solution, basically dispersed graphene oxide in water, so which is prepared by modified Humboldt method in our lab. So then, if we see surface chemistry of this graphene oxide, so this is a little bit dirty. So there are many different types of oxygen functional group. So it is not well defined. But so we can expect some kind of redox reaction with this kind of oxygen functional group and lithium-ion, right? The question is we can have this kind of surface redox reaction with the oxygen functional group on the graphene. And the second question, if yes, how can we effectively utilize this kind of the redox reaction? So to answer these questions, we prepared graphene oxide film using the vacuum filtration method. We just vacuum filter this graphene oxide solution so that we can get this kind of graphene oxide paper so on top of the membrane, so we can detach this paper from the membrane. So then you can see this kind of 2D layered structure of the graphene oxide film. So then we measure this graphene oxide film in the lithium cell. So as you can see, there is some capacity. So around 90 milliampere gram. But the capacity is not so high. And also, lay performance is very poor. So if as you can see, if we increase current density, the capacity is quickly decreased, right? So I believe this kind of the poor performance because of the low electronic conductivity of the graphene oxide. Graphene oxide is almost insulating, right? So to recover electrical conductivity, we need to partially reduce this graphene oxide. And second, as you can see, this is a compactly packed 2D layered structure, right? Probably electrolyte ion is hard to diffuse into this layer structure, right? So that's the that's the origin of the poor performance for these graphene oxide electrodes. To improve this performance of these graphene oxides, so we mixed with the functionalized oxidized fuel carbon nanotube with the graphene oxide. So we first prepared the dispersion, including both oxidized fuel nanotubes and graphene oxide. So then, we again apply the vacuum filtration process. So then, as you can see, these kind of the carbon nanotubes are inserted between the graphene oxide film layers, right? So we can get this kind of 2D alternating layered structures. So now then, so to recover electrical conductivity of graphene oxide, we partially reduce this graphene oxide at 200 Celsius for 2 hours under argon environment. So then, so we can expect some kind of the fast ion diffusion through this kind of the gap between the graphene oxide. So then, if we compare charge storage performance, so at the slow current density, the capacity has been increased from 80 to 120, right? Also, if we increase this kind of the current density, so we can get actually better lay performance, right? So then to further improve this performance, we decide to use the 3D graphene. So we can also synthesize this kind of the 3D ball-shaped crumpled graphene oxide using the aerosol spray pyrolysis method. So this is the shape of the 3D graphene. So then again, so we mix this 3D graphene with the functionalized carbon nanotubes. So after a vacuum filtration process, we can get this kind of the 3D hierarchically porous structure. So now graphene oxides are anchored so within the fuel carbon nanotube networks. So then if we compare performance, as you can see, the capacity has been increased. Now it's close to 160 milliampere gram. So now if we see rate performance, we can see significantly improved rate performance compared to other graphene oxide and other composite materials. So then this is because of the facilitated electronic and ionic transport through this kind of the hierarchically porous structures. So it is interesting, these two electrodes have the similar chemical composition. If we compare oxygen to carbon ratio, both have 0.07. Chemical structure basically almost same, but if we modify this microstructure, so we can improve both capacity and also rate performance of this kind of electrodes. Okay, so next, so let's remove the carbon nanotubes. So let's try to design the electrode material based on only graphene. So this is graphene oxide dispersion, right? So instead of the vacuum filtration process, we apply the hydrothermal reaction. So simply, so pour this graphene oxide dispersion into the closed vessel. So we just heat this vessel, so over just 100 Celsius. So then the phase of water becomes superheated phase, right? So basically, the phase of water becomes superheated vapor, and they can generate the, a proton. So then this proton can reduce this graphene oxide. So then the reduced graphene oxide can recover their sp2 conjugation network, right? So then the reduced graphene oxide have some kind of van der Waals and also Phi-Phi interaction. So they are self-assembled, so generating this kind of the graphene hydrogel. So then if we see surface chemistry, just graphene oxide has a high oxygen to carbon ratio, 0.42. Then if we simply increase this hydrothermal oxidation temperature, so we can reduce this ratio below to 0.05. So then if we see high resolution XPS peaks, so this graphene oxide film has dominant CO peaks, comes from the hydroxyl or epoxide group. But after hydrothermal reduction, we can see huge decrease of this peak. So basically, this indicates the recovery of the sp2 conjugation network of graphene. So then also we can control the microstructure of this graphene electrodes. So this graphene hydrogel, so if we just dry this graphene hydrogel in vacuum drying, so they shrink to this kind of particles. So then it is hard to make electrode with this kind of particle. So then instead of vacuum drying, so we use the freeze drying process. So then, so we can preserve this kind of porous structure. But if we see the density of this electrode is too low, 0.02 gram per cc, right? So as I mentioned, that the density is also important, the parameter for designing electrode materials, right? So if we consider the density of commercial activated carbon electrode is around 0.7 gram per cc. So then we use the different types of drying process. We first mechanically press this graphene hydrogel, then we apply the vacuum drying process. So based on this kind of two-step drying process, we can get this kind of folded graphene structure. So density is pretty high now, 0.6 gram per cc, comparable to commercial activated carbon. But this electrode still have this kind of some laterally developed porous structures. So then, if we measure charge heterology performance of this graphene electrodes, so this gray one is graphene oxide film. So if we reduce at 130, 180 Celsius, you can see development of this kind of oxidation and reduction peak. So interestingly, if we increase the temperature too much, so we can see decrease of this redox peak. So this is because if we increase this reduction temperature too much, so now we are removing some good or some active redox functional group also, right? So that means there is some optimum reduction temperature. So then you can see this kind of the graphene, reduced graphene oxide film has good capacity, so around 140, 50. So after reduction at 130 Celsius. So one of the distinct advantage of this organic material is high cycling stability. So we did cycling test up to 50,000 cycling tests. But actually, there's no capacity degradation. Actually, capacity is a little bit increased. So this is first cycling, this is the 50,000 cycling charging discharging curves. So as you can see, actually, the capacity has been increased. So this is because, I guess, during the charging discharging process, electrolyte ion can diffuse into the deeper side of electrodes, can find more electrochemically active surface area. Also, we collaborate with the Professor Seung Woo Lee here at MSc. So he calculated the redox potential of the various oxygen functional group using the DFT computation method. So as you can see, the graphene itself has some redox potential around 1.2 volt. So we calculate the redox potential of the carbonyl, epoxide, hydroxyl, so H plane, and also carboxylic acid group. So we also calculate the number of the different functional group. This case, we calculate the 1, this case 2. So as you can see, so as we expect, this kind of carbonyl group has the highest redox potential, around 3 volt. This is consistent with the basically experimental result, right? So we can conclude that this kind of carbonyl group is the main contributor for the redox reaction of this kind of the carbon-based electrode materials. Okay, so the next topic. So on top of this kind of nanocarbon, such as carbon nanotubes and graphene oxides, so we want to incorporate another redox active organic molecule. So let me show one example today. So here, so we use dopamine. So dopamine is interesting organic materials. So if we dissolve this dopamine in alkaline solution, so dopamine can be oxidized by the dissolved oxygen molecule. So they are gradually oxidized. Eventually, they are polymerized on top of any kind of substrate. So then, simply, we are mixing this dopamine with just pristine carbon nanotubes, right? Just mixing. So then, in alkaline conditions, we are just storing. So then, dopamine can be polymerized on top of this kind of carbon nanotubes, right? So we can create the very thin dopamine coating, polydopamine coating on the carbon nanotubes. So then, using the vacuum filtration process, again, so we can create this kind of the self-standing, flexible electrode materials. So then, so we can control the loading amount of polydopamine by simply controlling the concentration of dopamine or simply controlling the storing time of this dopamine. The question is why? Why we need to use dopamine, right? So then, actually, the exact structure of the polydopamine is still under debate. But people consider that this kind of 5,6 endoquinone is the major component of the polydopamine. So then, if we see structure of this 5,6 endoquinone, right? This molecule has 2 carbonyl group, right? Based on these 2 carbonyl group, if we calculate the theoretical capacity, this should be higher than 360 milliampere per gram, right? That's the one motivation. So then, if we see the microstructure of this composite electrode, this is just carbon nanotube network. So then, if we polymerize, so dopamine on top of these carbon nanotubes, so we can see the gradual increase of diameter of these carbon nanotubes. So as you can see, this is 30% of carbon nanotube polydopamine loading, and this 60% of the polydopamine loading. So if we compare the diameter of this carbon nanotube, you can see this one, polydopamine coated one, has a higher, larger diameter compared to pristine pure nanotubes. So then if we increase polydopamine loading too much, now we can see this kind of the sphere. This kind of sphere is basically polydopamine sphere. So they are synthesized based on the self-nucleation process if the dopamine concentration is too high. So then if we see a high resolution TM image, we can clearly see the formation of polydopamine film on the carbon nanotubes. So this is with the increase of the storing time. This is 15 carbon nanotube. After 6 hour storing, we can see the formation of the polydopamine. So also we can clearly see the uniform conformal coating of the polydopamine after 18 hours, right? So then, using the XPS, we can further confirm the incorporation of the oxygen functional group from the polydopamine, such as this kind of carbonyl group. And also we can see the incorporation of the various nitrogen functional group from the polydopamine. So then if we see electrochemistry, so this is the CV data. So as you can see, the first CV scan showing strong oxidation wave. So this is come from the electrochemical polymerization process of the adsorbed dopamine, but this quickly decreased. So we can get very strong redox peaks after a few cycles. So this is the steady-state CV of this polydopamine composite film. So interestingly, if we do potential-dependent CV scan from the low scan or low voltage region, so we can see gradual development of this kind of oxidation reduction peak, oxidation and reduction peak. So we believe this comes from so endoping process, the redox reaction between the oxygen functional group and lithium-ion. Interestingly, also we can see some development of the redox feature here at high potential region around 4 volt. So we believe this comes from the p-doping process of the polydopamine. So I will show some mechanism for this next slide. So this kind of polydopamine is redox active. So not only with the lithium-ion, but also with sodium-ion. So we can use this for both lithium-ion battery and also sodium-ion battery. So also, this polydopamine film shows a good rate performance by maintaining its redox feature up to 25 millivolts per second. So then, again, the Professor Seung Woo Lee at MSc calculate the redox potential of this kind of the polydopamine film. So we calculate the redox potential of this kind of 5,6 indole include this kind of carbonyl group, also this kind of the 5,6 dihydroxyl indoles, so which has this kind of hydroxyl group. So that, as you can see, if we see the calculated redox potential, it is close to 3 volts, right? So then, so we can see this kind of the 5,6 indoquinone is the major contributor for redox reaction. And so this 3 volt is pretty consistent with the electrochemical result. As you can see, we can see huge oxidation reduction peak at 3 volts. Also, we calculate the redox potential for this kind of p-doping mechanism by considering interaction between the anions between this monomer and dimer and trimer. So then calculate redox potential is in the range is around the 4 volts, right? From 3.7 to 4 volts. Then if we see so this kind of CV scan, so we can see this kind of redox features. So this is related with the p-doping mechanism with the anion, so electrolyte anions. So then if we compare discharge profile in lithium cell and sodium cell, so this gray one is just fewer carbon nanotubes, gives only 40 or 30 milliampere per gram in lithium cell and sodium cell. And by incorporating this kind of redox active polydopamine, so we can increase the overall capacity over 130 in lithium cell and 115 in sodium cell, right? But this capacity has been calculated based on the total mass of the electrodes, so including carbon nanotubes and polydopamine, right? So then if we calculate, if we estimate the capacity of the only polydopamine, so the capacity of the only polydopamine is pretty high. It's over 200 milliampere per gram in lithium cell and also over 200 milliampere per gram in sodium cell. Also, it shows very good rate performance. And also, we do cycling tests, so we can see stable performance up to 10,000 cycles. So basically, there's no change of charging-discharging profile. So between per cycle and 10,000 cycles. And also, we tested the self-discharging test. So we hold this electrode at 1.5 volt. So after self-discharging test, so we open the cell, so wash it with the solvent. So we can clearly see this kind of lithium peak. So when we hold at 1.5 volts. So this confirms the interaction between the oxygen functional group and lithium ions. So basically confirming the endoping charge storage mechanism of this polydopamine. So one of the weaknesses of this polydopamine composite film is the low capacity based on the total electrode mass, right? So only 120 or 30. So if we compare previous graphene, so that was the around 150, right? So then to overcome this kind of low capacity issue, so we use the different polydopamine functionalized process. So here, so we mixed dopamine with the graphene oxide dispersion together first. Then we apply the hydrothermal reaction. So then during the hydrothermal reaction, polydopamine coated on the surface of this kind of the self-assembly graphene oxide. So then as you can see, this electrode has pretty high porosity, right? So probably the density is pretty low. So we just mechanically press these electrodes. So we can get this kind of the compact, highly packed structure electrodes. The density is now 0.75 gram per cc. So we measure capacity. So based on the total electrode mass, now the capacity has been increased over 200, it's close to 250 milliampere per gram in lithium cell, also over 200 milliampere per gram in sodium cell. So we significantly increase the overall capacity. So based on the total mass of the electrodes by using this kind of the hydrothermal polymerization process of the polydopamine. Okay, so this is the last topic. So basically the last topic is the multifunctional energy storage device for flexible and wearable electronics application. So let me first introduce layer by layer self-assembly process. So basically, layer by layer self-assembly process is thin film formation process. So based on the electrostatic interaction between the negatively charged and positively charged species. So if we prepare this kind of negatively charged carbon nanotubes and positively charged carbon nanotubes separately, so prepare the solution. So then we dip the substrate alternatively into this positively and negatively charged solution. So this kind of carbon nanotubes can be self-assembled by the electrostatic attraction. So let me call this kind of the dipping here, let me call this is the one bi-layer cycle. So then if we increase this bi-layer cycle, so we can increase the thickness of this carbon nanotube on the surface, any kind of substrate, such as silicon wafer and also iTild coated glass. So we can linearly increase the thickness of this carbon nanotube film by controlling this kind of the bilayer number. So then this is SEM image, cross-sectional SEM image of the carbon nanotube film on the silicon wafer. So you can see conformal uniform thickness of carbon nanotubes, and this white arrow indicates interface between the carbon nanotubes and the silicon wafer. So this is the my PhD work during at MIT. So I first introduced this kind of carbon nanotube to a layer by layer system and demonstrate some carbon nanotube-based electrode for lithium-ion battery. So then the last year, Professor Jinan Cho from Korea University, he visited my group for 1 year. So then we developed the new types of the layer by layer self-assembly process called ligand-mediated layer by layer self-assembly. So instead of using electrostatic attraction here, so we use the ligand exchange reaction between the two organic molecules. So we prepare this kind of TRAN molecule. So this kind of TRAN molecule has 3 primary amine group. So we also prepare different batch. So different batch include metal or metal oxide nanoparticles, so which are stabilized by this kind of bulky ligand. So this ligand is tetraoctyl ammonium bromide ligand. So this ammonium group attached on the surface of this metal oxide nanoparticle, so gives some colloidal stability of this nanoparticle. So we first dip substrate into the this TRAN molecule solution. So then TRAN adsorb on the surface of this substrate. So we move to this kind of the nanoparticle solution. So then this kind of primary amine group has a strong affinity than this kind of ammonium group. So this primary amine group can detach this ammonium group, can adsorb on the surface of this gold nanoparticle. So basically, we can generate this kind of gold layer, nanoparticle layer on the surface of the substrate. So we can move again to this TRAN molecule solution. Now the TRAN can replace the remaining this kind of the bulky ligand, can adsorb on the surface of this gold nanoparticle layer. So then we move again to nanoparticle layer. Basically, by repeating this kind of layer by layer process, we can create the conformal and very thin coating of the nanoparticle layer on the any kind of substrate. So our goal is to design the flexible and wearable energy storage devices, right? So then generally people use paper or some kind of the cotton or some kind of the fabric as a substrate. But as you know, the paper and fabric are insulating, right? So we first convert this kind of insulating porous substrate to make the conductive porous substrate, right? So we convert this kind of the insulating paper to metallic paper by incorporating gold nanoparticles. So using the ligand-mediated layer by layer self-assembly process by repeating the trend and gold nanoparticle adsorption process. So after converting this kind of paper to metallic paper, so we further incorporate some pseudo-capacitive nanoparticles such as iron oxide and manganese oxide nanoparticles, which have high energy density. So this is the cross-sectional SM image. We can see the many filament of this kind of the paper. So then we can see the conformal coating of the gold nanoparticle layer, so around this kind of the fabric and also paper. So then this is a bare paper. So after repeating this kind of ligand-mediated layer by layer self-assembly, so we can convert bare paper to metallic paper. So if we see electrical conductivity, so after 16 bi-layer deposition, the electrical conductivity is pretty high, it's more than 230 Siemens per centimeter. So I believe this is the highest electrical conductivity ever reported for this kind of the flexible substrate. So then on top of this conductive paper, so we are incorporating manganese oxide and iron oxide nanoparticle. So this gray one shows bare gold-coated paper, so just conductive, but there's no charge storage performance. After incorporating 20.5 bi-layer of the manganese oxide, we can clearly see the increased charge storage capacitance. But one of the disadvantages, one of the problem of this kind of the metal oxide nanoparticle is their poor electrical conductivity. So we periodically incorporate this gold nanoparticle. For example, so we are deposit 3 layers of this manganese oxide, then we are incorporating 1 layer of the gold. So repeating again, 3 layers of the manganese oxide, 3 layers of gold. So we are repeating this kind of the layer by layer deposition step. So by incorporating gold layer between this manganese oxide layers, we can further increase the capacitance. If we see the specific capacitance, so without gold layer, the capacitance is around 500 farad/gram. But after incorporating gold layers, we can increase the capacitance over 700 farad/gram. So also we can precisely control the mass loading by controlling number of the bi-layer. Basically, we can do pinpoint control over the area capacitance by controlling the mass loading over this kind of the micro-scale energy storage devices. So we fabricate the full device. So basically, this is the manganese oxide-based positive electrodes, and this is iron oxide-based negative electrodes. So we use this kind of polymer types, gallium electrolytes. So we made package with the PDMS. So we do tests under bending and lapping structure, showing the stable performance. Also, we perform the cycling or stability test under flat and bending conditions, showing really good cycling performance. So when we compare this energy density and power density based on the unit area of this device, shows pretty high power and energy density compared to previously reported this kind of the flexible supercapacitors. So also we can simply increase this energy and power by incorporating more active materials. Okay, so this is summary slide. So we are trying to develop some redox active organic materials by considering scalability and also sustainability. So now we are trying to develop some multifunctional energy storage device by considering this kind of the flexibility and stretchability of the electrodes. So our goal is to design the next generation energy storage materials which have high energy density and high power density and excellent cycling stability. On top of this kind of performance, we are trying to add this kind of functionality to support fast evolving wearable and flexible device application. Okay, so thank you. So this is the
show the carbon became denser, and then you also their SEM image also shows kind of less porous. We would expect a lower surface area, VET surface area. So lower surface area would mean a smaller capacitance. But in all the CV curves that you have, I guess they are after you functionalize the nanotube, they became larger.
Yep. So that's a good question. So first of all, as you expect, there are two types of the charge storage mechanism, right? The first one is the double layer capacitance, as you mentioned. That's related with the surface area, right? So the other one is the pseudo capacitance or surface redox reaction between the oxygen functional group and lithium-ion, right? So then, if you see this pristine carbon nanotube shows only 30 milliamp per gram. So this can probably represent the double layer capacitance portion, right? But after oxidation, it's become 120, sometimes 150, right? So you can roughly estimate the contribution of the double layer capacitance and surface redox reaction, right? So then based on this result, double layer capacitance probably below than 10 or below than 20%, right? As you mentioned, there might be loss of some double layer capacitance, but so we have more oxygen functional group, right? Because we are incorporating more surface redox reaction, so we can increase the overall energy density, right?
So for the nanoparticle work, are they a challenge to synthesize, and how do you coat them uniformly over relatively large areas?
So basically, so let's say this kind of nanoparticle is dispersed in toluene, right? So then toluene is kind of non-polar solvent, right? Actually, so there's no electrostatic repulsion between this kind of nanoparticle. So then, basically, if we see this structure, so this kind of nanoparticle is compactly aligned each other, right? So because the first thing is there's no electro repulsion. The second thing is, as you can see, so we are removing most of this kind of the bulky organic ligand, right? So then make this kind of nanoparticle is close packed on the substrate, right? So then that's the one of the reasons we can get really high electrical conductivity also.
Is it a challenge to disperse these particles over the entire paper?
No, actually, it's pretty easy, actually. So I think so basically, generally, so before this work, so people use the polyelectrolyte. So for example, let's say gold nanoparticle. First prepare the charged gold nanoparticle. So then we prepared another charged polymer, right? So then we are depositing first nanoparticle and polymer, nanoparticle polymer, right? So then in between this kind of the nanoparticle layer, so there are bulky polymer, right? So then the electrical conductivity is not so good. So now we remove all of this kind of bulky polymer and bulky ligand. So we can decrease the distance between the gold nanoparticle. So basically that can maximize the electrical conductivity and communication between this kind of nanoparticles. Yeah.
When you talked about the surface roughening of the carbon nanotubes,
Yes.
Is there any negative effect on mechanical performance as you worry about, let's say, in lithium-ion batteries because of that?
Actually, it is. So, but there is some kind of the optimum oxidation time. For example, let's see here. Pristine 2 hour, 4 hour, you can see a gradual increase of the oxygen to carbon ratio. So eventually, after 6 hours, right, something happened, right? So actually, there is cutting of these carbon nanotubes. They are basically mechanically like degrade because too much oxidation process, right? It's kind of the maximum like the oxidation time, right? So basically, as you can see, this roughened, eventually like the oxidation radical is cut these kind of nanotubes, yeah. You mean this kind of surface quality?
Yeah.
I think.
They're not pure SP2 or SP3 like you guys.
I think that's probably this graph shows some kind of the answer, right? So as you can see, so this is oxidation time, right? So 2 hour, 4 hour, 6 hour, right? So then, so you can see the oxygen to carbon ratio is 0.1, 0.2, 0.17, right? So then, as you can see, this performance is like the increase, but saturate, right? So this showing is a good correlation between the capacity and the amount of oxygen functional group, right? But this is just one factor, but we also probably can study some, let's say, the rate performance, but there's no correlation for this. But there might be some correlation between the oxygen functional group, the amount of oxygen functional group onto rate performance. But if we only consider just average capacity, it shows really good correlation.
One last question. Okay, let's thank Professor Lee one more time.
Thank you.